Hello, it's Malcolm here, and in this screencast I'm going to talk to you about the types of models that applied mathematicians use when they study or model the world around them. The reason I want to talk about these models is because it's another way in which you can reflect upon the processes of applying maths to other disciplines. We've already seen the modelling cycle, and we will think about that, but we will also now talk about types of models. Before launching into our discussion of the types of models that you might use, let me point out that there are two factors that will definitely influence the modelling that you choose. The first factor will be what is the purpose of your modelling? What is it about the situation that you're trying to understand? And there are four possibilities that I can think of. The first one is you want to test if something works, so usually you've just got one scenario and you want to see is it possible or is it not possible. You might know something about the situation you're modelling and you want to find out what happens in cases that you don't know about, so you want to predict outcomes. You might want to explore what happens if changes are made. So you have a situation, you model it, and then you make some changes to it to see if you can get something else. And finally, you might want to explain why something works, in which case you make your model, compare its results to what you observe, and then the inputs to your model then will tell you something about why the situation works. So they're the four things that I can think of for why you may want to model. And of course, what you want to model then will influence what type of model you use. The other factor that's relevant is the type of model that you choose to use will be the model that you've had the most experience with and have confidence in using. Now, for example, if you're a computer programmer, you would like to use computer models a lot, I would imagine. In your case, you haven't had much experience in any of the models, so we have to start from scratch. I'm sure there are many different ways of categorizing models, but here we go with one way of categorizing them. So in this set, the first category is that of physical models. And as an example, imagine that you've got a hall and it's going to be used to host a major tourism exhibition. The question is, what is the best way to arrange the various exhibitors? Well, naturally, you'd have to have a discussion of what we mean by best. But imagine that you have sorted out what you mean by best, then you could probably use a scale floor plan of your hall and use little squares to cut out each of the exhibition sizes, and you could move those squares around on your floor plan to get a better idea of what is the best way to arrange your exhibitors. Best could be fitting in the most exhibitors, best could be having the best flow through the venue, and so forth. There's lots of different ways you can do, but the scale floor plan, that's a physical model, would actually help you in understanding that situation. Notice in here that if you changed venues, you'd have to change your model completely. You'd have to go and get a new floor plan and so forth. So physical models usually have a testing aim in mind. They say, here is a scenario, is it possible or isn't it? And physical models are usually limited in what they can change or what you can vary. The next category of model are what we're going to call empirical models. Empirical literally means based on experience, but for us it'll mean they're models built up on the basis of data and nothing else. So purely empirical models do not have any recourse to any underlying theory whatsoever. So as an example, imagine that we're going to tie a simple overhead knot in a piece of rope. How much do we expect the rope to get shorter? Well, in the way of all good modelling, we'd start off by having a look at what factors might be important here. So it might be what's the rope made out of, how thick is the rope, what else can we think of? Is the rope wet, is it dry, does it matter how tight we tighten the knot, and so forth. There's lots of factors that we can put in here, lots of factors. So imagine for the minute that we're just going to concentrate on the relationship between the rope, how much the rope's length has decreased, and the diameter of the rope. So if we were to do an empirical model, we'd have to go away and we'd gather some data on how much does the rope decrease for various diameters of rope. And if we could, of course, you get rope with made out of exactly the same material. We'd tie it on exactly the same day, so that the weather conditions are the same, the humidity is the same, the temperature is the same, and so forth. And we'd get some data, and we would record that data. So here's some data that I've gathered, and of course, as you can imagine, I didn't actually go and do this. I got this off the net. But the experiment that I read, they said they measured how much the rope had been shortened 3 to 5 times, and they averaged each of them to try and get some sort of good measurement technique going along. And then we made a plot of that. And as you can see in the plot, down here, there's a big dip in there. So it looks like that maybe that piece of rope here was made out of some sort of different material, or who knows. But if we ignore that piece of data, then the rest of it seems to look like it goes nicely like a straight line. So having got our data and had a look at it, we can create a model in the form of a formula by fitting a straight line that goes through the data, ignoring that rather spurious point. So if we let L be the length by which the rope is shortened in millimetres, and let D be the diameter of the rope, then by looking at that data we can come up with the model that L is equal to 8.0 D plus 1.2. Given that this formula comes solely by looking at the data and nothing else, this is an empirical model. Now what can we do with the model? Well, we had some diameters in our data. We can now use this model to predict how much the rope would be shortened for diameters that are not in our data. And so in other words, we can use this model for prediction purposes. And that's the usual use for empirical models. The next category of models are statistical models. And really these are empirical models, and they're based on data. But the difference to the purely empirical model is that the data that we get usually has a fair variation in it, and to get out what you want, you have to do some sort of manipulations of the data, and that manipulations will involve all sorts of statistical methods. So as a simple example, just say we wanted to investigate the relationship of do people that exercise more have lower resting heart rates. Well, to do that, what we would do is we'd gather the data, i.e. the amount people exercise and their heart rates. We'd draw a graph, and then we would fit a line to that graph. The way we fit this line is due to statistical methods called correlation. So in this case, we can see that the line is negatively correlated. As your exercise goes up, the heart rate goes down. And so that's an example really of a statistical model. Perhaps a better example might be something like who is going to win the next election. In a case like this, we would do some statistical inference, it's called. So what we would do is we'd work out a characteristic of the whole population by taking a sample. So we'd go around and we would, say, interview 1,000 people, and we would say that from that 1,000 people we're going to predict what the whole election is going to do. Sometimes these things are good, sometimes they don't work so well. But that's an example of a statistical model. And statistical models are used mainly for predicting what's going to happen. They don't necessarily talk about cause and effect. They don't necessarily tell you why those things are going to happen. Okay, so our next category of model are simulation models, and really they're nearly always computer simulation models. But these types of models are really good for analysing situations that have randomness, uncertainty and unpredictability, because with a computer model you can run the model 1,000 times and get an idea on average of what's going to happen. So for an example, in a supermarket there are a number of checkouts, but how does the manager decide how many to have open? Well, a simple way to do this would be to create a simulation. And let's do a really rudimentary simulation here. So let's assume for the minute that it's a maximum of 6 customers arrive at the checkouts at any minute. Of course, in a real model, you'd actually get this data from observations of your particular supermarket. Imagine it takes 1 minute to serve each customer. Of course, that's not quite correct, but that'll do for our model. And customers spread out evenly across, in this case, 3 open checkouts. And so what we're going to do is we're going to simulate the arrival of customers by rolling a dice and have the number that comes up when you roll the dice being the number of arrivals in that minute. So let me actually do a simulation, and here it goes. In the first minute I rolled a 2. There are 3 checkouts, so that both people who arrive get served, and so there's nobody in the queue. In the second minute, 5 people arrive according to my dice, so 3 of them get served, and so 2 of them in the queue. In the third minute, another 1 arrives, so there are already 2 in the queue, so that makes 3 in the queue, but they can all be served because we have 3 checkouts, so there's nobody in the queue. And away you go, and you keep rolling the dice and you can work out what's going on. So in this particular case, it would seem that 3 checkouts seems to be about right, because the queue doesn't seem to be growing, and there aren't idle checkouts so that your staff aren't sitting there doing nothing. So if we ran this simulation 1,000 times and took averages, we could tell whether, assuming that your initial data is okay, whether 3 checkouts is a good number to have open. And this is indeed what a lot of big businesses actually do, a lot of this simulation. The beauty of simulations is that they're cheap, easy to run, a computer program. They allow lots of flexibilities. You just have to change something in your program, and often they are the simplest and indeed the only way of studying certain very complex situations. So simulations are in fact a very important class of modelling. And for us to make, certainly doing it with dice and so forth is not very satisfactory, but we can get into simulations using something like Excel, spreadsheet programs like Excel, or if you want to get more sophisticated simulation programs, there are purpose-built ones, but a free one is NetLogo, and it can do a lot of other mathematical stuff besides, and I think I talk about that in the appendix. Okay, and the final category in our types of models is going to be what I call theoretical models, and a lot of what the high school teachers would have done in their mathematical modelling classes would have been theoretical models. But theoretical models are abstract versions of reality, and they're usually looking at explaining why things happen. So in other words, you build your model and you see if the data actually agrees with what you observe, and if it does, then the way you built your model tells you what's important in that particular situation. So let's go back and have a look at that simple overhead knot problem that we did earlier by an empirical model. This time we're going to take the theoretical approach. So we're going to try to understand how it is that the diameter affects the amount by which the rope is shortened. So to do this, let's have a little look at an overhead knot. There's my attempt at drawing an overhead knot. But now what you have to do is imagine that you're looking at this from end on in my simple little theoretical model here. So here it is from end on, and you can see in here that these are the bits of rope here, and this part around here is the outside of the knot, and so it's the outside of the knot will be the amount by which the rope has shortened. So what's that length? Well, we can see that it will be this semicircle here, and the radius of that semicircle is the same as the diameter of our rope. So there'll be 2 of those because there's another semicircle over here, and then there's this straight bit here which will also be this length here, 1 there and 1 down the bottom. Both of those are the same as the diameter of the rope. So adding all of those up, we will say that the length of the rope is 2 pi plus 2d. 2 pi plus 2 is about 8.2, thereabouts, so 8.2d. If you remember back to our empirical model, we got 8.0d plus 1.2. So this model here is slightly differently. It doesn't have a plus term, but that makes sense because it says when the diameter is 0, your rope won't get shortened by any amount. So the fact that this coefficient 8 here, or 8.2 here, is the same as our empirical model tends to suggest that our simple theoretical model here is on the right track. And so to finish off our discussion of types of models, there's just a couple of things to note. Firstly, as always, models don't necessarily fit nice and neatly into any one category, and I may not have every type of model that's sitting in there. So models may be used for more than just the purposes we mentioned, and they may go across some or all of the categories. But we've got a good start to our introduction to the type of models that we've got. And the second thing is, if it's possible to model a situation using two completely different approaches, like we did with the knot problem where we did it empirically and then we did it theoretically, if those results agree, then you're going to proceed with some confidence that your models are on the right track, and you'd probably only proceed with whichever model was easiest to work with. If they don't agree, then you've got to go back and try and work out why. And of course, in so doing that, you'll probably better understand the situation as well. So that's where we'll leave our introduction to modelling, and we will now get you to have a go yourself. Look forward to it.